Chapter 6.6 DeMoivre's Theorem and Nth Roots. Every real number can be plotted on a number line. Every complex number can be plotted on a complex plane. On a complex plane, we have two axes. We have a real axis and an imaginary axis. So the real numbers are plotted along what corresponds to the x-axis, and the imaginary numbers are plotted along what coordinates with the y-axis. So if we're going to plot 2 plus 3i, we go 2 over on the real axis and 3 up on the imaginary axis. Try this. Plot the following points: 1 plus 4i, 2 minus 3i, and negative 3 plus 2i. If we have the complex number z equal to a plus bi, and we want to find the distance from the origin to z, we would take the absolute value of the complex number. And the way you find that is just take the square root of a squared plus b squared. The absolute value is called the modulus of the complex number. The plural of that is moduli. So you can see here the graph of our complex number z, which is equal to a plus bi. A is the real portion and bi is the imaginary. So we've plotted the point there, and you can see the distance from the origin to z is r, which is our absolute value or modulus. We're going to take our complex number a plus bi and put it into trigonometric form, which will be r times cosine theta plus I sine theta. R is our absolute value or modulus of z, which was the square root of a squared plus b squared. Now I'll show you how we'll actually use that formula. We're going to find the trigonometric form with theta being between 0 and 2 pi for the complex number 1 plus the square root of 3i. Step 1 is to find r, or the modulus. We know that r is equal to the square root of a squared plus b squared. Our a is 1, our b is the square root of 3, so we have the square root of 1 squared plus the square root of 3 squared. 1 squared is 1, the square root of 3 squared is 3, 1 plus 3 is 4, and then we get the square root of 4 is plus or minus the square root of 2. As we discussed before, in polar coordinates, it doesn't matter whether it's positive or negative, we'll get the same points from it. So we'll just call r equal to 2. Next, we want to determine the quadrant for the point. Looking at our complex plane, we have 1 plus the square root of 3i. 1 is the real, the square root of 3i is the imaginary, so we go to the right 1 and up square root of 3. The point will lie in quadrant 1, so the sine, cosine, and tangent will all be positive, and theta will be between 0 and pi over 2. Step 3, determine theta. Tangent of theta is y over x. The y is the square root of 3, the x is 1, so tangent of theta is the square root of 3. And remembering from the unit circle, tangent is going to be square root of 3 at pi over 3. Now that we have our modulus and theta, we can plug it into the equation. Our equation is z equals r times cosine theta minus I sine theta. R is 2, theta is pi over 3, so we get 2 times cosine pi over 3 plus I sine pi over 3. So this is a summary of it all. R is 2, theta was pi over 3, and 1 plus the square root of 3i is equal to 2 times cosine pi over 3 plus I sine pi over 3. Try this. Find the trigonometric form of 2 minus 2i. I've listed out the steps for you. Give it a try. Moving on to the next related concept, finding the product and the quotient of complex numbers. If we have two complex numbers, both in trigonometric form, and we want to multiply them, we multiply the moduli, r1 times r2, and then the cosine and the sine, we add the angles there. So z1 times z2 equals r1 r2 times cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And this is what it looks like when you actually are using it. If we have two complex numbers in trigonometric form, we have 4 times cosine pi over 4 plus I sine pi over 4, and z2 is square root of 2 times cosine pi over 6 plus I sine pi over 6. Here is our formula again. Plugging the numbers into the formula, r1 times r2 is 4 times the square root of 2, and then we get cosine pi over 4 plus pi over 6 plus I sine pi over 4 plus pi over 6. In adding together pi over 4 plus pi over 6, we have to get a common denominator of 12, which would make it 3 pi over 12 plus 2 pi over 12, giving us 5 pi over 12. And we repeat that with a sine function as well. Then using the calculator, yay calculators, we can find the cosine of 5 pi over 12 and the sine of 5 pi over 12. Multiply both of those by 4 times the square root of 2, and we get our complex number 1.464 plus 5.464i. Try this. Find the product of z1 and z2 and write it in standard form. Because the cosine of 30 degrees and cosine of 60 degrees are known functions, known values, we can do this as an exact value for an answer. Pause the video while you work this out. Let's look at z squared. Z squared is z times z. Writing these in trigonometric form, we'd have r times cosine theta plus I sine theta times r times cosine theta plus I sine theta. Using the equation we had earlier, we multiply r times r, we get r squared, and we add the angles. So we get cosine theta plus theta, which is 2 theta, plus I sine 2 theta. And here we have a picture of what it looks like. We have z plotted in there in the first quadrant, and if we are going to square it to get z squared, we will end up with r squared, so the radius will be squared, and theta will be doubled. Now let's look at z to the third. If we have z to the third, that's just z squared times z. So we'd have r to the third cosine 3 theta plus I sine 3 theta. And this leads directly to DeMoivre's theorem. Nice French sounding name there, DeMoivre. So he says that if you're raising a complex number z to any power, what you'll get is r raised to that power times cosine the power times theta plus I sine the power times theta. So now we're going to put it to use. We're going to find negative the square root of 3, 2 minus I 1 half raised to the fourth using DeMoivre's theorem. The problem is this is not in trigonometric form. DeMoivre's theorem came from trigonometric form, so the first thing we have to do is to put this into trig form. The first thing we're going to do is plot the points to find the quadrant. When we plot them, we find that we're in quadrant 3. And this will tell us that theta will lie between 180 degrees and 270 degrees. Now we need to find the value of r. r is equal to square root of a squared plus b squared. Our a was negative square root of 3 over 2, and our b was negative 1 half. When we square those, we get 3 over 3/4 plus 1/4. 3/4 plus 1/4 is 1. Square root of 1 is 1. Now we want to find the value of theta. We did this in a little different order than before, but the order really doesn't matter. We're going to use the tangent function. Tangent is y over x. So our y was negative 1 half. Our x was negative square root of 3 over 2. Because we were in quadrant 3. So we have negative 1 over 2 times negative 2 over square root of 3, which gives us 1 over the square root of 3 for a tangent, and tangent is 1 over square root of 3 at 7 pi over 6. Now that we have our r and our theta, we can plug them into the equation. The argument of z, all that means is the value that you'd have, like f of x. X would be the argument of f. So this is z of theta. So the theta would be 7 pi over 6. The modulus is 1. Those are the things we figured out before. And so therefore, plugging it into the equation, we get z equals cosine 7 pi over 6 plus I sine 7 pi over 6. Remember, it was all multiplied times the modulus, which was 1. All that was just to put it into the trigonometric form. Now that we have it in trig form, we can use DeMoivre's theorem, which I will put back on the next slide to refresh your memory. So here it is again. When whatever power we're raising it to, the r gets raised to that power, and cosine and sine, we multiply theta by that value. So we're taking z to the fourth, so we multiply 4 times 7 pi over 6 for both the sine and the cosine. Remember, the modulus was 1. 1 to the fourth is 1. So we get cosine of 4 times 7 pi over 6, which reduces to 14 pi over 3, plus I sine 14 pi over 3. 14 pi over 3 is coterminal with 2 pi over 3. So cosine of 2 pi over 3 is negative 1 half, and sine of 2 pi over 3 is square root of 3 over 2. So we get our final answer there, negative 1 half minus I square root of 3 over 2. I'll make it a little easier on you. I'll give you the problem in trigonometric form already. Take 3 cosine pi over 4 plus I sine pi over 4 to the 5th power.